Okay, good morning. Let's begin. So first of all, I have posted your midterm grades. So you're supposed to be able to see what letter grade based on my calculations you have right now. The way it was done is, as I said, every week users submit homework or quizzes. So I kind of deal with it as being weekly grade. So then for each week, I had we had 6 weeks, I believe, of weekly assignments. So I looked at the 6 grades I had, which is a mix of homeworks and quizzes, depending on what you did this week. And then I picked the 5 best scores from it, which was 50 points. Then I did the same for the discussion. I believe we had 6 weeks of graded discussion. So I again dropped one lowest score of one of the discussions, another 50 points. So 50, 50, it's 100. And then you had a test, which was another 100 points. So that means up to right now, you could have earned 200 points in this class. So what I did is I summed all of those together and I found out the percentage. If you remember, the way you do it, if the cumulative points you got are X and they're out of 200, to get the percentage, you actually do X divided by 200 multiplied by 100, which is pretty much half what you got. And this is how your grade was calculated. Then I used a very basic scheme of determining if it's like A, B, C, or so on. And yes, I did use pluses and minuses. Now, for some of you, for example, the grade was, I don't know, 79.6. I still rounded it to 79 and put it as C plus. Or for example, if somebody got 89.6, same result, even if it's 89.8 or 9. Why? You're still missing a tiny bit, like less than like 0 point something out there, but you still need it, correct? And it's easier to lose points than to gain them. So I really wanted you to see like this I have right now, for sure. The one which is round up is not there yet. However, when I calculate the final grades, this is where I round traditionally. So if it's above 0.5, it's going to be rounded up, and otherwise it's going to be rounded down. But this is for final grade only. For now, this grade you got, letter grade, it does literally nothing. It's just a point for you to know where you stand. So if you see a good grade, like A, keep on doing the good job you're doing right now, come to lectures, do work, and hopefully we will continue doing as great. However, if you are not doing so greatly right now, start working, okay? Questions? Okay, algorithm 5. As I said, everybody who wants to see algorithm 5, welcome to my office hours. I'm not going to be testing you on algorithm 5. It just takes too long of a time to do it. However, I did want you to play with it. I think the most common concern with the algorithm 5, yes, this is algorithm 5. I even remember it. So the main thing nobody is doing is write down the problem you're trying to do. Look at what algorithm computes. Your algorithm 5, this is from homework, supposed to be computing this. Due to it, you can determine that your B is 3, your N is 644, and your M is 645, for example. This is an exercise I have in a textbook. Then this is your step 1. So you set up your problem, you realize what are your inputs. This is your input. However, the input requires N to be in binary format. So the second step you're doing is you're converting 644 to binary to get this. And those are your A's. So those are like your A0 and so on. Over here, I also calculate K minus 1 for you so that you know, and the way you calculate it is you literally look how many binary places do you have? And in this case, you have 10 places. So the last one, since you start with indexing 0, is 9. And then you literally do your algorithm. An important point, if is only done when condition is true. However, power changes in all iterations. So look at the examples they have. Take a picture of this page I have out here. This is the exercise below algorithm 5, step by step, where I explain what's changing and what's not changing. It's not finished up, but hopefully that should be enough. What you do an exact same thing in your homework assignment. Now, this is an important algorithm. It's used a lot in like number theory, and so it's a good one to know. It's like part of public encryption. Did any of you heard about RSA? Since like RSA is very commonly used for the encryption scheme, it's all the RSA scheme is explained in our textbook, I believe in section 4.6 maybe. If you're interested, read about it, but you're going to see what it's all built upon calculating those type of things. So this algorithm is important. It has a real life usage. And this is why I kind of gave it to you as a homework assignment, so that you're going to be introduced to it. However, it's a lot to remember for the test, and I'm not going to be testing you on that. However, you still should do it. I still might check this problem on a homework assignment. Now, what will happen if this last digit out here, if A0 is going to be 1? If A0 is 1, then this line is not going to be x equal to 1, correct? Because in this case, my A0 is going to be 1, my condition is going to be true, and I'll have to do x is equal to 1 multiply 3, so x is going to become 3, and I'll keep on going. Does it make sense? So, and then here, since it's not changing, it's also going to be 3 in it. This is the way it's going to work. So you'll have to kind of run it one step at a time. You'll have to build like a table or line by line thing, and you just need to follow the directions of the algorithm, okay? Play with it. And again, welcome to office hours with that question. But we really need to move on because we are kind of falling behind. So today we must finish up some of the sections, actually most of chapter 5, because we already almost finished up 5.1 last time. So to remind you, of mathematical induction. The idea here is we have a propositional function, and we want to show that it's true for all n. So not just in one case, it's not just for two numbers or anything, it's true for any value of n. Maybe there are some conditions to it, but we really want to show it's true for everything. Now, since it is true for everything, I cannot really say, okay, let's look at them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like it's going to go to infinity, correct? So I need a different tool of how to prove it. The way we prove it is we actually use this principle. We're saying, okay, if I know that this is true, and I have a rule saying k true implies k plus 1 true, that is going to give me everything. The reason for it is because I know for sure the first one is true. Then this is true for any k, so including for 1. So knowing 1 is true implies 2 is true. So this is how I can conclude 2 is true. And then if 2 is true, then 3 must be true too, correct? So this is kind of like the example with the books I had. Remember when they were falling down? The books. So pretty much the only thing I needed to know is I needed to know this falls, correct? Out from the falling. And then we also need to know that if I have in the middle two books, if this one falls, this one must be falling too, like it's going to really kick it and it is really going to make it fall. So I only need to know for any book in the middle K, the next one is going to be also falling. Does it make sense? So if I know that I pushed K, then K plus 1 is also pushed and also fell. That's all I need to know. And then you're going to have like a dominoes effect of falling dominoes, okay? Or falling books in our case. So I already did a couple of examples for you, and we're going to continue with even more examples. Okay, where's my new page? Sorry, it's hiding something here. Nice. So last time we did an example of 1 plus 2 plus n is equal to n plus 1 over 2. Like, remember, the other way to write it is summation from I equal 1 to n I is equal to n plus 1 over 2. Those two are equivalent to each other. Those are just same problems written in a different notations. As said in the last class, I prefer this one when I work, because this way I see how many elements I have. But you can use either notation you use. In the discussion today, the question will have these notations. I want you to try and unscramble it first into notations like this, and then work with it. It's going to make, and it has it as a theme, so you'll figure out what I'm talking about when you get there. And today we're going to do more exercises. So I want to prove n cubed minus n is divisible by 3. How can I prove it? Well, there are different ways of doing it. You can try and use like with the division to 3, it is going to have different remainders and things. So you can decide that n is like divisible by 3 or not, or has remainder 1 or the remainder 2, but it's going to be a nightmare. The best way to do it is, since I have an n here, and I have it for all n bigger equals 0 or bigger 0, it doesn't really matter. I want to prove it by induction. This screams induction, okay? This screams induction because I want it for any n, and I kind of have it here. So my base case can be either n equal to 0. In this case, I'm going to have 0 cubed minus 0 is going to be 0. And of course, 3 divides 0 because everything divides 0, correct? My other options can be 1 if I want to do it. So it's going to be 1 cubed minus 1 is also still 0 and it's still divisible. I just really want you to see it now. I only need one of those two base cases. I definitely in this case do not need the third one, but I really want you to see that it works because it's going to be z, which is 8 minus 2, which is 6, and guess what? 3 divides 6. It is working for numbers too, not just for 0. Okay, so it is good question. It is working. How do we prove it? So the next thing I'm going to do, I always call it Iowa, IA, yes. So this is induction assumption. Okay, so this is what I assume. So I'm going to assume for n equal k, k cubed minus k is divisible by 3. Now, when I use it, when I use keywords like division or even or so, I always need to use definition, mathematical definition to help me out. So this means exists t such that k cubed minus k is equal to 3 multiplied t. How did I get it? This is the definition of this divisibility, correct? I can represent it as 3 multiply something, right? And this something has to be integer, okay? And now I'm going to do is, which is an induction step. So this is where I'm going to do the inductive proof. I want to prove n equal to k plus 1 is true. What does it mean? It means I want to prove k plus 1 cubed minus k plus 1 is divisible by 3. Okay, how can we do it? Well, you're not going to like it, but we're going to open up the parentheses. So k plus 1 cubed minus k plus 1. Now, can I do most of those operations in mind? Yes, I can. Moreover, I also remember the formula of k plus 1 cubed. Does it mean I can avoid all of my parentheses, do everything in one step? Probably not. And plus, you probably don't do it like I do it every semester, correct? So you probably don't remember it as well. So be careful. When you substitute instead of nk plus 1, don't forget the parentheses. The most common mistake is going to lose the minus on negative 1. And then all of your mathematics is not going to work out. And guess what? You're not going to be able to prove anything. So be careful, don't rush, put your time to put your little parentheses and do all the operations carefully. So this is pretty much the same as k plus 1 squared minus k minus 1, which is k plus 1, k squared plus 2k plus 1 minus k minus 1, which is k cubed plus 2k squared plus k squared plus 2k plus 1. I'm just literally opening up in the parentheses. Minus k minus 1. So you already can see that I can cancel this one and this one. You can already see that I can cancel this one and this one. So what do I get? What I'm going to get is k cubed minus k plus 3k squared plus 3k. Okay, I'm going to take back the cancellation over here. I'm going to take this beautiful minus k to be over here, and this k with this 2k are going to give me the 3k. Okay, that's how we separated it. Why? How the heck do I know what to do? So look at it. You always need, this is why it's important to write it down. You can always go back and see, I know something. So always look at what you plan on substituting. So you know you can use k cubed minus k is divisible by 3. So what you need is you need to somehow figure out, how do I get out of this disaster something which is going to be substitutable? And in this case, do you see it? I got an exact same box. So this is why I wanted it to be into the form of k cubed minus k. And I didn't want it to be to the form of k cubed plus 2k instead. Does it make sense? I was kind of trying to achieve this thing. I was trying to get to it. I was trying to see the same thing. So now what we can do is using our induction assumption, and this is why the shortcut is so good. Using our induction assumption, I can substitute it to be 3t plus 3k squared plus 3k. And guess what? I can factor 3 here, correct? Pretty easily. And guess what? I have 3 multiply L, where L is equal to t plus k squared plus k, which is differently integer, correct? Hence, 3 divides k plus 1 cubed minus k plus 1, correct? So what we really have is we proved that n equal to k plus 1 is true, correct? And so we proved original statement by induction. Okay, next. Another one. Assume I want to prove 7n plus 2 plus 8 2n plus 1 is divisible by 57. For all n bigger or equal 1. Base case. So let's look at it. 7 to the power 1 yes, thank you, Cody, for answering. You're right. This is coming from the induction assumption. This is why I wrote IA on the equal sign. So for n equal 1, we're going to have 7 to the power 1 plus 2 plus 8 to the power 2 multiply 1 plus 1, which is going to be 7 to the power 3 plus 8 to the power 3, which is actually going to be 855, which is 57 multiplied 15. So guess what? Divisible by 57. Now I'm going to do induction assumption. So Mohammed, here is a similar assumption to the previous one, and this is what we're going to be using again. So we're going to assume for n equal k, 7k plus 2 plus 8 2k plus 1 is divisible by 57. So exists t integer such that 7k plus 2 plus 8 to the power 2k plus 1 is equal to 57 multiplied t. This is again from chapter 4. Remember the divisibility properties, right? So now we're going to be doing induction step. Proof for n equal k plus 1. So we want to prove 7 to the power k plus 1 plus 2 plus 8, 2. Again, I replace the n everywhere by k plus 2. So we literally substitute, instead of this little n, I substitute k plus 1. That's what I'm doing. Okay? And I want to show it is divisible by 57. So in order to do it, what we're going to do is, again, we're going to play with powers. And look carefully at what I'm going to be doing, because you're going to be using this trick at homework assignment and today during the discussion. So now what I need is I'm going to mark it in a very bright blue out here. But this is the thing I know, correct? So where I really want to get to is I actually really want to have something as 7k plus 2 and 8 to the power 2k plus 1. That's what I want. So let me look at it. So what I really have here is that, correct? Not exactly what I want. And what we have here is that, right? I just opened parentheses and added everything. It's not exactly what I want. So now I'm going to put it to the form I want. So in order to get out of 7k plus 3, the 7k plus 2, I have one extra 7, which I'm going to put like this. This is just properties of powers, correct? You add powers, so this is still the same. Now in here, again, I have actually 2 useless 8s, so it's going to be 8 squared multiply 8 to k plus 1. Agreed? So the other way of writing it down is 7 multiply 7k plus 2 plus 64 multiply 8 2k plus 1. Agreed? Yes. Now, the most common mistake is trying to say, well, it's 57 multiplied t. No, it's not. Because I have too many 7s to the 7 to the power k plus 2, correct? So I somehow need to have into the parentheses 7k plus 2 plus 8 to the power 2k plus 1. They need to be like one body scrambled together, and I can multiply something by it, but I really cannot have just like, you know, addition and extra numbers in it. So look at it. 64. Can you represent 64 as 7 plus something or 7 minus something? Yes? No? Can you do it? 64 is 7 plus x. What is my x? 64 is equal to 7 plus 57. Do you agree? How do I know that's what I want? I plan on factoring the 7. Okay, so I'm trying to figure out how can I factor the 7 out. So actually this one is going to be 7 plus 57, 8 2k plus 1. And guess what? Now our life is going to be beautiful, because what we have is we have 7 multiply 7k plus 2 plus 7 multiply 8 2k plus 1 plus 57 multiply 8 2k plus 1. Now those ones, they really have the same 7, correct? They are both multiplied by 7, so I can factor it. I can represent it as 7 multiply 7k plus 2 plus 8 2k plus 1 plus 57 multiply 8 2k plus 1. And this is where I'm going to draw my blue boxes, and I'm going to say, okay, here is my blue box, correct? Here is, I finally got to the place I wanted. I finally have those two together with the addition, nothing is in between. So I can replace it with 57. So using induction assumptions, this is what IA is on this thing, so that you know this is what we use. I'm going to put it as 57 multiply 8c plus 57 multiply 8 to the power 2k plus 1. But now look at this beauty. I have 57 here and 57 here. So guess what? I can factor it out too. So I have 7t here plus 8 2k plus 1. So guess what? I have 57 multiply L, where L is the 7t plus 8 2k plus 1. And of course, it's an integer because t is integer and 8 to the power is integer, correct? Because k is positive integer. So guess what? We are done. It is divisible by 57. Do you see it? Because it's 57 multiply something. Now, one other way to see this thing over here is like that. If you think about it, what I have is I have 7 multiply 7k plus 2. Look at it. What it really is 7k plus 2 plus 7k plus 2 plus 7k plus 2 7 times, correct? Agreed? And then in here I can say I have 8 to the power 2k plus 1, 64 times, correct? $64 times. Agreed? That's what I have. Now what I can do is I can pair them up. I'm going to take this one and pair it together with the first one, and I'm going to put 57 instead of it. Then I'm going to grab the next 2 and so on. I'm going to get 7 pairs like this, correct? Yes? And on each of those pairs, I can use my assumption. And then how much, if I took 7 out of here, how much 8 to the power 2k I will have? The 57. So this is just the visual way to see how they pair up and what's left. The numbers are ugly, so I really will not going to write you the whole 57 out here or 64, but you kind of get the idea, correct? We just pair them up. Okay. On that note, you're ready to get your homework from section 5.1. And you're going to be doing for me 5, 8, 11, 16, and 32. And on the side, you're hopefully going to be able to see it because we move on and we're going to go and talk about section 532, which is called strong induction. So in previous chapter, we talked about mathematical induction. It was a type of a proof. Now, strong induction is very similar to mathematical induction, but it has a stronger assumption. We assume a little bit more than in traditional mathematical induction. So what we did in the previous one, what we said is, what I need to know is this will fall, correct? And we need to know k falls knocks k plus 1, correct? If k is then k plus 1, that's what we want, correct? Those are my assumptions. Now I'm going to have something very similar, but instead of assuming only that, I'm going to assume not just if k. Instead, I'm going to say all of them for all up to k fall. Does it make sense? So instead of assuming just one before we fell, I'm going to assume everybody before we fell. Okay? So it's a bit stronger. However, guess what? It's the same thing, right? To some extent. And I'm going to explain to you why we need it sometimes. Because we are going to have some problems which will not only need knowledge about one previous term, but it might need to know something in the middle, but the middle element first, okay? So in this case, strong induction is required. So let's write it in the official way. What we want is we want to prove Pn is true for all positive integers, and you again need two steps. Basic step, P1 is true, which is no different from conditional induction. And then inductive step, you're going to say assume P1 and P2 and Pk true, then prove Pk plus 1 is true. So the whole difference here is instead of assuming Pk, I assume everybody before me. Do you understand the difference? But the steps are really the same. We're going to be writing almost the same things. The only thing is we are going to change our language a little bit. Okay? Oops.
And this one is going to be a hard one. Okay, so let's see. N is bigger than 1, N is integer, N can be written as product of primes. This is, remember the fundamental theorem of arithmetics. Remember how we had it as like product of primes and we had it as a unique, but I never proved it to you. We only discussed it and did some examples. Now it's time for us to prove it. Okay, let's prove it. So base case is going to be n equal to 2. See, I do not have equality sign here because we generally do not consider one being prime. Okay, so n is 2. So 2 is prime. Hence, and hence work, correct? This is representation using the primes, correct? Yay. Next, assume this is my inductive assumption, which is a strong assumption. Assume for 1 to up to k, all of those can be represented as products of prime or just prime numbers by their own. Now, inductive step, prove k plus 1 can be represented as product of prime. Okay, so case 1, k plus 1 is prime. Because k plus 1 can be a prime number, correct? We are arbitrarily pick k, so k plus 1 can be prime, correct? If k plus 1 is prime, we're done, correct? Because it's just prime number, correct? So, yay. Now, case 2, k plus 1 is composite. What composite means is not prime, correct? Then exist as t, both integers, such that k plus 1 is equal to s multiply t. Agreed? And this is where the big difference between traditional mass induction and our stronger assumption comes to place. In this case, it's not really k, correct? We're not really using k. In this case, we found some numbers and both s is less than k plus 1 and t is less than k plus 1. Do you agree with it? Because it's one number multiply another number, they have to be less than k plus 1. Agreed? Now, it's not directly a number before me, but I assumed it's true for everybody, correct? So, oops. So by induction assumption, both S and T can be represented as products of primes. Assume S is equal to product I is equal 1 to n of prime i's, and T is going to be product. P is kind of like the sum for like the sigma notation. This is the notation for product. J is going to be 1 to M P J. So those are some primes, correct numbers, where actually those are going to be QIs. Okay, I do not want to use the same letters. Okay, and PI are primes for all I in between 1 and n, and QI are primes for QJs for all j in between 1 and m. So now let's look at k plus 1. K plus 1 is say s multiply t. So I now have that. But actually, let's think about it. Each of those p's and each of those q's is a prime, correct? So I literally now have a product, correct? It is still, I have multiplication between all of them, correct? So I literally have, in sigma notations, I can call it as ijkl from 1 to n plus m of p prime else. All of them are primes, correct? So literally it's just a larger sum of all primes. Hence, k plus 1 can be represented as product of primes. And we are done. Now, last question for today. We are going to talk about STEM problem. And you're going to practice it at the discussion too. So I'm telling you that any n bigger or equal 12 can be represented using 4 and 5 cent postages. So what I'm trying to tell you that I can give you, you're going to tell me, I want like n cents in postage. And in my box C, I only have postages of 4 cents and 5 cents. I'm telling you, no matter what number you're going to ask me for, I'm going to be able to give it to you using my postages of 4 and 5. I do not have postages of 1. I do not have postages of 2 or 3. I only have box of postages, either 4 cents or 5 cents. And I'm telling you, no matter what number you give me, 55, 100, 200, I'm going to be able to give it to you only using my 4 cent and 5 cent postages. How can we prove it? So in this case, my base case is easy. I need to show you how to get 12. So 12 is 3 postages of 4 cents. Now I'm going to do a couple for you because I will need to go back a couple of steps. So 13 is 4 and 4, 8, 8 and 5, 13, perfect. 2 postages of 4 and 1 of 5 cents, correct? Because 2 multiplied 4 is 8, 8 plus 5 is 13. Now, so here's how I can do it. Now my induction assumption can be done for n less or equal k. Proof for k. Now, k is equal to k minus 1 plus 1. Agreed? Yes? So now this number can be done using postages, correct? So k minus 1 is less actually than k. Agreed? You can do the same thing by saying k plus 1 and doing something like that. Looking at the k, okay? It depends if you're going to put equal here or not, okay? So we're proving for k plus 1 because I put equal. So k plus 1 is k plus 1, and k is less than k plus 1. Hence, by induction assumption, can be represented. So k is equal to s multiply 4 centages plus c multiply 5 centages. Case 1. There is at least one 4 cent postage. take it and replace with 5-cent postage. The number I got now is K plus 1, correct? So literally I have the box for the K. It has amount of postages here, amount of postages here. Now the next one is case 2. And this case 2 is going to have only 5 cents. Now, if it is only 5 cents, I have at least 3 of such 5 cents. Why? Look at my numbers. I have 12, 13, correct? I do need to show you 14. We will come back to it. But then it's 3 or 5 cents or larger, correct? But 3 multiplied 5 is 15, correct? Replace replace them all. 4 multiply 4 cents, which is going to be 16, correct? So instead of 15, I now have 16. So I got my K plus 1 and I'm done. The only thing I only need to show you is the 14. Do you understand why I need to show it to you? Because 14 doesn't have it. But for the 14 is going to be what? 5, 5, and 4, correct? 2 5s plus 1 4 cent. 5 and 5, 10. 10 plus 4, so we're done. So after 15, I will either going to have at least 3 5-cent postages for multiples of 5, or it's going to be combination. And I showed you how to get rid of combinations, correct? So homework from this section. And I know I'm tiny bit over the time. I'm really, really sorry about it. But it only has 2 questions for you to do, which is a good thing, correct? 4 and 32. And we will talk about 5.3 next time. Enjoy the discussion section today. Have a good day. One second.